All right, next on the agenda, it is our privilege to introduce Miguel Munoz, who works with Dole. He joined Dole in 2001 as a research and development scientist in banana technology. He now oversees the design and implementation of lab and field experiments in the areas of crop physiology, banana breeding, biocontrol, micropropagation, and fruit quality. His role supports general managers and production managers with data analysis and agronomic recommendations. He obtained his bachelor's degree in agronomy and crop science from the University of Costa Rica and his master's in plant biotechnology. He carried out research on rice viruses at the Center of Research in Cellular and Molecular Biology at the University of Costa Rica within the Rice Biotechnology Network. He was awarded a fellowship from the Rockefeller Foundation and obtained his PhD in plant molecular biology at Cornell University in 2000. Returning to the University of Costa Rica, Miguel researched protein analysis for plant viruses and genetic engineering prior to joining Dole. It is my privilege to welcome Miguel, and I look forward to hearing what he has to say, particularly around the new banana program that we have as part of PEP. Welcome.
A couple of months ago, Nick called me and asked me if I would be willing to give a seminar about banana diversity. And when I asked about what kind of audience would be, he said, well, there's going to be a bunch of budding scientists as well as accomplished ones and leaders in their fields. So even though sounds very intimidated, I decided to join the fray, and here I am. And even though English is not my mother language, I hope that I can get you very interested in the topic that I'm going to talk about, which is going to be banana diversity. So here I go. First of all, let me introduce the company I work with. As Dr. Bauer said, I worked in Dole. I joined Dole in 2001, and our primary goal is to produce fresh and nutritious vegetables and fruits from different sources around the world and distribute it to customers everywhere. We are probably one of the few large fruit growers in the world. It has its own research and development department overseeing many aspects of the operation, from soil scientists all the way to post-harvest science and everything in between. We take good pride, or high pride, in the fact that we grow very healthy products with the best agronomic there is, as well as respect for the environment, including the social environment, as well as for workers. We grow, well, we are not a new company. Actually, our roots goes back to the 19th century. We started in Hawaii in the 1850s with pineapples. And in Central America, we started as a standard fruit company in Honduras back in 1890. And we have revenues above $6 billion. And we are one of the largest growers and marketers of fresh fruit and vegetables around the world. We do business in more than 90 countries, and our workforce includes above 90,000 employees, as well as 24 seasonal and temporary employees. So it's quite a large organization. Now, in the case of Central America or Latin America, we basically produce We supply bananas and pineapples from the tropics, mainly Central America and the northern part of South America. We grow bananas one of the strategies of these companies is to expand and search from different areas in order to reduce the risk of hurricanes or loss of fruit because of natural causes. So we supply bananas from Central America as well as South America. So we have operations in Guatemala and Honduras as well as Costa Rica. We also supply for independent growers in Colombia and Ecuador, and we also grow organic bananas in Peru. In the case of pineapples, most of our operations are centered in Costa Rica as well as Honduras, and the headquarters are located in Costa Rica, where we oversee operations of the whole region. Not only we grow our own products, but we also ship, and we have a large fleet of vessels that go to the U.S. and to Europe and other places, carrying both pineapples and bananas. And all of that, it's having in mind our commitment to the satisfaction of our customer. In this slide, as you can see, a very humble and simple banana can be shipped and boxed in many, many different types of boxes and different types of presentations. It all depends on the consumer and the customer. Whatever they want, we basically bend our back in order to accommodate for their needs. The reason why I'm here, and I hope I can entertain you for at least 45 minutes, is to talk about banana diversity and the challenges that are in our near future. As you know, most of you are quite aware of just one type of banana, and I'm going to show you what really bananas are. And when I'm going to use the word banana in a very liberal way. I'll describe, or it describes both bananas, cooking bananas, plantains, and different sorts of most species. Even though we are familiar with just one type of banana, there are more than 75 wild-type species and over 1,000 edible bananas distributed or subdivided into 50 groups. So it's quite a large crop. We might be familiar with just one type of banana, the Cavendish one, and what is not for export purposes, the exotic bananas, that are actually staple food in many parts of the world. And that includes fat bananas, colored bananas, thin and slender ones, you name it. Unfortunately, the banana industry has been focused only on one type of banana, despite the fact that there's a lot of diversity out there. And probably, as you will see in the next presentation, the possibility to offer different types of bananas, plantains or cooking bananas, with different nutritional attributes. When we see how bananas are produced in the world, it's one of the largest crops there is, with over 150 million tons produced per year. Interestingly enough, some of the countries that are the largest growers, they also are the largest consumers of bananas. For instance, Brazil on one hand and India, they are the largest growers of bananas, but they are the largest consumers as well. And when we talk about consumers, we're talking about that diversity that you saw in the previous slide. It's basically what they eat or what they consumed on a regular basis. And for export purposes, most of the production is centered either in Southeast Asia, Philippines mainly, and Central America and South America. When we look at the consumption patterns in the world, we can see countries where they consume large amounts of bananas, and as I mentioned, could be bananas, cooking bananas, or plantains, especially in Africa and Southeast Asia. But lucky for us, North America as well as Europe are also the largest consumers in the world, with an average around 35 to 40 kilograms of bananas per capita in the U.S. And as I said before, one of the problems is if you go to a supermarket, most likely you will see baby bananas. In some occasions, you can see red bananas and the regular bananas in different presentations. See the regular banana, organics, bags of different sorts, and different post-harvest technologies with the bags. So that's pretty much it. That's pretty much the diversity that is offered in the market. So the presentation, or the spirit of this presentation is to look beyond this type of banana and see what's there in the growing areas. Before I do that, I'd like to introduce the banana plant, because usually, being a tropical plant, we don't have a clear picture of what it is. Basically, the banana plant is a large herb. It's a perennial plant. It produces between 1 or 2 bunches of fruit per year. The stem actually is very small. It's right here. It's called a corm. And right on top of the corm, there's a bundle of leaf sheets, very tightly packed together. And from the corm, you can see a complex system of roots, primary, secondary, tertiary, and very fine roots that anchors the plant and allows the plant to absorb water and nutrients. The pseudostem, actually it's not a trunk, it's a pseudostem. It's composed by leaf sheets, and the blades are very, the leaves or the blades are very large, and it allows high levels of transpiration rates for a quick uptake of water and nutrients. During the vegetative phase, bananas produce a large number of leaves, around 30, 35 leaves per plant. At some point, there is a hormonal signal that makes the shoot tip to switch from vegetative to a flower. At that point, the plant responds by releasing the growth of what is called suckers, which is going to bear fruit in the next generation. Once the shoot tip turns into flower, the flower stalk grows through the pseudostem, as you can see over here, and bears a bunch. The bunch is composed of 2 different types of flowers, female flowers, and in fact what we eat or what we consume are large ovaries from the female flowers, and the male flowers, once they shed the pollen, they're useless and they fall off. So that's basically, in a nutshell, the anatomy of a banana plant. It is important because when we refer to different types of bananas, I will mention some of these terms. Before I go on, let me do a very quick and very brief history of the banana business. Bananas originated about 90 million years ago in the jungles of Southeast Asia with different species. Fully seeded, totally fertile, that were able to cross between and among those species. And later on, because of some mutations, plants were able to produce what is called parthenocarpic fruit. That is fruit that does not bear or contain any seeds. And for the first time, you can have a banana that can be consumed without problem. Now, human groups roaming all the way from Africa to the Southeast Asia and Polynesia came across this diversity of potentially new crops. And as they migrated, they carried different types of bananas, plantains or cooking bananas. And they distributed back to India and back to Africa, where there is a second site of differentiation or speciation. Later on, in the times of the Greek Empire, bananas were introduced into the Mediterranean Sea, and the Arabic seafarers were able to get bananas from India all the way to Africa, and they established plantations in the islands in the Atlantic, the Madeira and the Canary Islands. And to make story short, when Columbus traveled to America and the second travel, they brought bananas and plantains for the colonies that would start in America. So it's bananas has been transported by humans through a process of domestication and introduced in many different environments. Now, how come we have a banana business as it is today? It is because of serendipity. Basically, two businessmen, Lorenzo Baker and Minor Kidd, were the ones who started the whole business. Lorenzo Baker was taking some fruits from the Caribbean and Central America back to the United States. And he came across, in one of the islands off the coast of Honduras, a very odd-looking plant, basically bananas. And he introduced it, or took it to the U.S., to New York. By the time they were having the International World Fair back in 1890s. And it was a tremendous success. I mean, it was a tropical fruit wrapped in foil, $1 per piece at that time. It was something totally new. And simultaneously, Minor Kidd was invited by the government of Costa Rica to lay out the railroads. Unfortunately, the government was cash-strapped. The tax revenue was very small. So at some point, the government decided to craft a deal with Minor Kidd. And the deal was as follows. He would be entitled to exploit any land 20 kilometers from both sides of any tract he laid for a cost of $1 per acre for 100 years. So he started looking for alternatives on how to work with to create a business because of all this land that was available. And one of the things he took advantage of was that in order to build the railroads, he imported workforce from Italy as well as from China, but they couldn't adapt to the harsh tropical conditions. So he went to Jamaica and got workers to work in the railroad construction. Interestingly enough, the Jamaicans brought bananas along with them because they wanted as a staple fruit. So simultaneously, as Lorenzo Baker introduced bananas as something new as a curiosity, Minor Kidd was needing something to grow in the land that was leased from the Costa Rican government, and all of a sudden, it all made click. So as he started laying railroad tracks in Costa Rica as well as in Central America and South America, he started growing bananas as well. And he built a whole empire based on the ability to produce bananas all year round and shipped all the way to the Gulf of Mexico and the East Coast. And this was the beginning of the first large monoculture in the tropics. Essentially, in a matter of few years, they went back to a few acres to thousands in Costa Rica and Panama first, and then Honduras. And it was probably one of the first and the most organized tropical crop there were at that time. And the plant they used was called Gros Michel, or Fat Mike, or Big Mike. This plant, or this fruit, was so sturdy that they could carry the bunches as such without removing the hands. It was sold as bunches. And the thing is so thick and so strong that they can stand scratches and everything. Unfortunately, a few years after they started the business, they started observing in farms in the border between Costa Rica and Panama symptoms of wilt. And they didn't know at that time what was the cause, but it turns out that somehow fungus, soil-dwelling fungus, was introduced from Southeast Asia, and it's called Fusarium Oxysporum cubense, race 1. This fungus is able to attack the plant, going through the roots and clogging the vascular tissue, so the plant isn't able to absorb water and nutrients, and dies within a matter of months. Unfortunately, this fungus is equipped to kill the plant very quickly, and it produces 3 types of spores: one of those spores called chlamydospores are able to remain viable in the soil for decades. We have areas that were contaminated at that time in 80, 90 years ago, and you cannot grow Gros Michel in those areas because the chlamydospores are still viable there. They didn't know exactly how the disease worked, so they hired plant pathologists to figure it out. And at the end, none of the measures they took, including soil disinfection and everything, they couldn't stop the disease. So the only way they had was to cut down and clear down forests and expand the farms, the banana plantations, in order to get away from the disease. Unfortunately, the seeds, the vegetative tissues they're using for banana multiplication were already contaminated. So the disease spread throughout Latin America as well as South America. So they moved to the Pacific side and carried the disease as well. So at some point, they figure out there must be a change in variety because otherwise the industry would collapse. And that realization was the beginning of the banana breeding process. Unfortunately, bananas are totally sterile. They don't produce, 99.999% sterile. They don't produce seeds. The sterility, the female sterility is almost complete. So breeding bananas is a very difficult task. So they started in Jamaica, in Trinidad and Tobago. The British started what is called the Imperial Agricultural College in the 1920s, and they started breeding bananas without knowing much of the basic genetics and cytogenetics of bananas. And it took at least 20 years to get the first hybrid because they didn't know how to do it. And I'll give you some statistics. You need at least to pollinate 3 million flowers in order to get a handful of seeds, at least 20 seeds. So it's labor intensive and it's very unpredictable. So, and as I said, in the 1920s, this botanist, Ernest Chisman, started the first breeding program, and they were able to produce within 20 years 2 hybrids, Bottles Alta 4 and one called 2390. These were the first 2 hybrids that were with some tolerance to Fusarium. Now, United Fruit Company, which was the largest banana company at that time, they knew they had to do something better, but they didn't have any germplasm available for the breeding program. So they hired 2 botanists, Paul Allen, as you see the picture right here, and Dr. Oxley, and they were sent to Southeast Asia to come through the center of origin, looking for as many wild-type and land races or exotic bananas as possible. And they assembled, over a course of 8 years, a collection of more than 800 accessions that were transferred to Central America and became the basis for the banana breeding efforts in Latin America. And they come through, they went to the Philippines, they went to Borneo, they went to different places. Unfortunately, they didn't collect anything from Africa or from India. So these collections were partial in the sense that the accessions or the diversity from these 2 places are underrepresented. Once they analyzed the data, once they analyzed the morphological traits of all these collections, they came up with the hypothesis that basically bananas are composed or hybrids between 2 species. One species is Musa balbisiana, and the other species is composed with different subspecies called Musa acuminata, and there were different types. Malacensis, Microcarpa, Sabrina, Erans, Banksy, and Truncata. And at some point, since the 2 species are fertile and are able to cross with each other and within each other, they produce a large number of hybrids. Those hybrids produce seeds. They are not edible. But at some point, some of these hybrids went through a process called parthenocarpy that I mentioned before. That is the development of fruit without fertilization. And in this case, you end up with something that is edible because it doesn't set any seeds. So you have, at this point, crosses between Balbisiana and Acuminata, and there's the second phenomena, which is polyploidy. Not only you have something that is parthenocarpic, but at some point they went from diploids to triploids to tetraploids, and with different sets of chromosomes from Acuminata and from Balbisiana. Now, if you look at the Balbisiana type, it's more like a plantain, and the Acuminata is more like a banana. So when you have a hybrid, you have something in between. Something that might look like a banana, but it tastes like a plantain, or something that looks like a plantain, but tastes like a banana. As I said, humans that went through these areas, they basically selected different types of fruit depending on their needs and carried as they migrated along or were hopping from island to island, they were taking these varieties along with them. And not only that, they keep selecting for better traits, more edible, larger fruit, things like that. And eventually, some of these groups went back to Africa, taking with them different types of bananas. So, in a summary, basically what you have at the basis of bananas is wild-type bananas that are fully fertile, non-parthenocarpic, and nowadays, because of the process of domestication and selection, you have a banana that is fully parthenocarpic without any seeds. So this is basically a process of having fertile species that were able to produce natural hybrids. Once these two phenomena, parthenocarpy and polyploidy, took place, as well as mutations, humans start selecting and domesticating these varieties, taking those varieties as long as they migrated. So, in summary, Dr. Allen, he proposed that bananas that we have today are basically the product of the crosses between Malvaceana and Musa acuminata and everything in between. So you have different types of non-edible wild-type species that are able to cross. At some point, because of parthenocarpy, they were edible, and at some point as well, you have different levels of ploidy. On these larger fruit, polyploids, humans start selecting for different characteristics. So now we have what is called the Musa acuminata edible diploids or triploids, which includes the desert bananas we have today, babies and the regular Cavendish. You have polyploids that have two sets of chromosomes from acuminata and one from Balbisiana, that basically it's something more like a banana with some traits of plantain, and that includes plantains, something called silk, awak, and parata bananas, which are the bananas consumed in Brazil. When you have a different constitution, genomic constitution such as this one, triploid that has one set of chromosomes from acuminata and two from Balbisiana, basically you have more like a plantain type, and that includes plantains called sabah, as well as cookie bananas. As it stands today, this classification by Simmons and Shepard, it's based on ploidy. What you have is diploids, edible diploids derived from acuminata, two sets of chromosome AA, or you have ABs, a hybrid between A and B, or you have triploids such as the Cavendish and the Gros Michel, or you have AAB, which is basically bananas with some traits from plantain, or you have the opposite. You have one A and two Bs. So as you can see, the genetic constitution of bananas is quite complex. it is now recognized that not only there are A or B chromosomes, but also some other species from Musa ciscocarpa and Musa textilis that provides genomes S and T. And there are also hybrids in between A's and B's with S and T's to make things more complicated. But from the consumption point of view, most of the bananas we consume today belong to the diploid or triploid group of A's, or derived from Acuminata, as well as triploids that includes ABBs or AABs. So basically that's what most people consume in Southeast Asia, or selections such as the one that I mentioned, diploids and triploids from Acuminata. The germplasm collections were distributed in different parts of the world, and this is a complex map that indicates all the activities related to banana breeding and banana research. Basically, what we have here is 3 active breeding programs, one in Central America, in Honduras, one in Brazil, and one in Africa. The first one, FIA, in Honduras, is mostly focused on developing desert bananas, whereas the Embrapa program is mostly focused on developing alternatives to what they call prata banana. And prata banana is something in between a banana and a plantain, but it's what they consumed. Whereas in the case of Africa, most of the efforts are on breeding for improved plantains. Unfortunately, most of these programs are underfunded, and there's a lack of collaborations between, or partnership between the private sector and the public sector. There's a second group of research activities that basically includes the French group. The French have been working in cytogenetics as well as the molecular genetics of bananas. And they also established in Belgium, in the Catholic University in Leuven, one of the largest repositories or collections of bananas in tissue culture. So you can access, you can just go through a catalog and request any variety that you want to test in the field. And there's a third tier of labs that are mainly working on biotechnology and genetic engineering. We're talking about Raham Meristems in Israel. They've been working for the last 20 years in GM bananas, as well as a lab in Guangdong University in China. And recently, a laboratory by James Dale in Queensland have been working and producing genetically modified bananas resistant to Fusarium wilt. So to make the story short, we came from Gros Michel as the main variety, and because of Fusarium race 1, they started breeding for resistant to Fusarium. Okay. By serendipity, when they started looking for a replacement or diploids in order to start the breeding program, they came across a variety that was previously present in different botanical gardens, and that was called the Cavendish bananas. And the Cavendish banana was totally resistant to Fusarium race 1. And the fact that that banana can be grown very easily, it was probably not the end, but the efforts for breeding was stopped for some time because the companies no longer had the need to breed for every banana. I mean, it was a godsend. Now you have a Cavendish banana that can be grown in areas that were abandoned because of Fusarium killing Gros Michel. And that was in the 1950s and 60s, and they started with 2 different subclones, one called brand name and the other one Robusta, and that's pretty much the basis of today's bananas plantations. So brand name was grown into millions and millions of plants and introduced in the different banana growing areas. And with the advent of tissue culture technology in the 1980s, different private labs start producing large amounts of bananas. And because of the fact that mutation rates in bananas are very high, they were able to select and to pinpoint or identify what is called some clonal variants with higher production potential. And in our case, in the case of Dole, we have selected something called an Equatoriano or Ecuador dwarf. It's a selection from Granane, and it produces quite a large bunch, between 30 to 55 kilograms per bunch, that allows you to produce between 3,000 and 4,000 boxes per hectare per year. It's quite productive. It's a dwarf type, less than 4 meters tall. Has a short return cycle, so you can produce close to 2 bunches per year. It produces a fair amount of suckers, so you can keep growing and producing your plantation every single year. You can select a sucker out of 3 or 4 developed very early on. Finger length, which is a critical issue, as well as curvature. It has a very nice conformation, has an excellent flavor. The ripening behavior is quite predictable, and packability is excellent. And as you can see, this is one of our selections. We have a program going throughout Latin America looking for individuals that are standing and what we call elite lines. And as I mentioned, because of instability or because of mutations, including transposon rearrangement within the genome, one common theme in banana is differences in plant height. We started with regular Cavendish that in the 1950s were close to 6 meters or 18 feet tall, and the clone that we keep selecting for is a Granane, which is close to 3.5 meters or 9 feet tall. That makes a lot of difference in terms of the agronomics in a banana plantation. It's very easy to bag and to remove flowers of the bunch in a smaller plant as opposed to a very tall variety. But because of the fact that a Cavendish banana is not a cylinder, but it's more like a funnel or triangular shape, we had to accommodate large hands, medium hands, and short hands into different packages so we can cater the needs for different customers. So we basically specialize our packing orders in order to get the most boxes out of a single bunch. And we even started large micropropagation facilities in Central America in order to take individual elite plants and multiply them into millions using tissue culture techniques. So eventually what we end up is a very large monoculture, hundreds of thousands of hectares, basically growing exactly the same plant. From the genetic point of view, it's a nightmare because it's a monoculture. Every single plant is exactly the same as any other plant. So one plant, a banana plant in Guatemala or Costa Rica is exactly the same as one in the Philippines or Ecuador. But it was quite productive, so everybody was happy. Unfortunately, guess what? In the 1950s, they were observing that when Cavendish bananas were grown in subtropical areas, mainly South Africa or Taiwan, because of cold stress, they could observe wilting symptoms, and they knew it was because of Fusarium, but it was in response to this cold stress. Unfortunately, in the 1990s, they observed the same symptoms without any predisposition factor in the Philippines, and it was a strain of a fungus, the same Fusarium wilt, Fusarium exportum, that was introduced from Indonesia. And unfortunately, this time, we don't have a replacement. We don't have a Cavendish falling from the sky. We have to build or breed for a different variety. And just as an example, these are pictures taken from the Philippines. As you can see, 2 plants already infected. And they were exactly the same symptoms that they observed with Gros Michel and Race 1 back in the early 20th century. They follow exactly the same pattern of dissemination. As you can see, some spots over here in the middle of a farm that are cleared without any banana plants. And those areas, and basically the plants are being killed, the soil gets infected, and you cannot grow any Cavendish banana for the future unless you have a replacement. So that's an issue, and the problem is this is a disease or a pathogen on the move, and it doesn't move by itself. It's moved by or transported by people. The initial focus was in Southeast Asia, but from here, it's been spread to southern China, to Australia, to the Middle East, and recently, 5 years ago, to Mozambique. And probably it was because of contaminated plants or contaminated soil in the shoes of Filipino workers being hired in these countries. So our worries are that eventually some of these samples of this disease will made to the Americas, where the disease is absent nowadays. Unfortunately, many of the banana technicians, scientists, soil scientists, and plant pathologists, they go back and forth to the Middle East as well as to Southeast Asia as part of their professional and technical duties. So eventually, the disease will be introduced into the Americas. What are the tools we have, or what are the choices we have now? We have basically only 3 choices. One is to do a breeding program, basically classical breeding, with the assistance of market-assisted selection. Basically, use genetic tools that we didn't have at the beginning of the 20th century, so eventually we can breed for a better type of banana. We can also take advantage of the fact that we can induce mutations in bananas and try to come up with a more tolerant banana. Actually, the Taiwanese have been able to produce varieties out of Cavendish that are slightly tolerant. They die at the end, that they can allow you to produce for 3 years. And there's also different projects centered on genetic engineering, basically GMO banana, which is a tough proposal for different markets, including Europe. But at least the Chinese are working on that, and they have very interesting results. When we go back to breeding again, there is a problem, and it's that you have to overcome sterility. Remember, Cavendish bananas are 99.999% female sterile. So trying to make a cross with a regular banana is a very tough proposal. Not only you have to do by hand very early in the morning, there is a time frame of only 2 hours. Otherwise, the pollen gets dehydrated. So it's very intensive labor in a very short period of time. You have to pollinate hundreds, if not millions, of seeds of fruit in order to get a few seeds. Not only it's very hard to get the seeds, but the embryos within the seeds have to be rescued because otherwise they won't germinate. So you have to do what is called embryo rescue and put it in tissue culture. And once you have those plants, that's just the beginning of the selection process. As I said, let's put in some statistics. You need 20,000 bunches, which is close to 3 million fingers, in order to get just 20 plantlets for field evaluation. So just do the math. If you want to do a selection on 100 plants, you need close to 12 million fingers pollinated. So it's a very tough task. So one of the things people in the breeding process, in the breeding business of bananas, find out is that you have to somehow cross a disease-resistant banana with one that has nice characteristics of flavor and post-harvest. The problem is if you do wild species, wild-type diploids, the result will be a diploid with very inferior characteristics. So one thing they found out is you need to spend at least 20 years in order to come up with the best diploid. And that process takes, as I said, at least a couple of decades. Once you have an improved diploid, so basically you have to go back and forth between wild-type diploids, you might be able to cross it with triploid cultivars, such as the Cavendish banana we want. The problem is the triploid banana, it's almost sterile. Remember, you hardly can see any seed in a regular banana fruit. But let's assume that you can do the crossing. Eventually, you end up with something called a tetraploid because you're crossing a triploid with a diploid. Tetraploids, unfortunately, have some fertility, but they also can set some seeds. So from the consumption perspective, it's not an alternative. So you have to go back and cross this tetraploid with a diploid in order to get a triploid. So, and if you're not confused, believe me, this is very confusing. So you end up with an improved triploid, but that takes at least 3 rounds of crossings. The problem is every step in the breeding program, you are selecting against fertility and selecting for parthenocarpy. So that means that every single step is tougher than the previous. And I'll give you an example of how this works. This one over here, Pisan D and Calcutta 4 and Pisan Jariwaya are wild diploids. They are the ones that started the whole breeding process. Those are the ones that were collected by Paul Allen in Southeast Asia. The other ones, the ones with the name SH, are improved diploids. So they are the ones that can be used for crossings. From here down to here, it takes about 20 to 30 years, okay? And once you have the diploids, you're ready to go. You can cross with a triploid, and even though the chances of getting a hybrid is so small, at least you have something in your hands. Now, because of this process, it takes a lot of time. The breeding programs keep these diploids as jewels of the crown, so they're not easily available. And I'll give you an example of the products of crossing. For instance, this one is called Pratana with this improved diploid, and they got 2 hybrids over here. So the thing is, you can do the crossings, you can do the breeding, but it takes a lot of time and a lot of effort. And not only that, it's not as straightforward as just doing 3 crosses and that's it. You have to go back and forth in order to improve the diploids. Then you go to a second round before you do the selection. Altogether, it takes between 25 to 30 years to get a new hybrid. And there are different types of alternative schemes that people over the years have tested. This is one, which starts with diploid improvement. Remember, this is 20, 25 years of work, and then they cross the diploid with a triploid and produce a tetraploid, which has to be crossed with the improved diploid in order to get the secondary triploid. This is the scheme most people are using now. And there's another one in which you take a diploid, you do chromosome doubling in the lab. Now you have a resistant tetraploid, you cross it with an improved diploid, and you end up with a triploid. Remember, triploids are parthenocarpic, they are sterile, they are the ones close to the bananas we want to consume. The alternative would be to look into exotic bananas and see if there's any chances of replacement. Unfortunately, we don't have anything that can replace Cavendish banana so far. So the only way would be either to engage into mutation breeding, classical breeding with the assistance of markers, or genetic engineering. There's no other way. In the meantime, we at Dole have one of the largest germplasm collections private collections in the world, and we have at least 4 things. We have exotic bananas, naturally occurring mutations, and we have elite lines. And I just want to go through very quickly through a series of exotic bananas just to show how diverse could these bananas be. If this collection was built over the course of 20 years, and the idea was to enrich the collection with things with different colors, different flavors, different resistant to pests and diseases. and eventually introducing to the market. We have failed so far. We have tried 3 times, and unfortunately, it's very hard to beat Cavendish bananas. I mean, it's highly predictable. It's one of the cheapest fruit in the market. Is from the post-harvest point of view, is very, I wouldn't say easy, but it's quite straightforward to put it from the tropics down to the market. And I'll show you some examples of things we have. This is what is called baby banana or golden banana. This is probably one of the first parthenocarpic, diploids, edible fruit that was domesticated by humans in Southeast Asia. Pisana on the other hand, and if you go to Thailand and India, probably this is the type of banana you will get. It's a diploid, and there are also triploids that has 2 chromosomes of acuminata and 1 from Balbisiana. It's has one of the nicest flavors, and one interesting feature, it doesn't brown at all. I mean, if you cut it, if you use it in a fruit salad, it'll remain white for 3-4 days without problem. It's one of the best flavors I found among bananas. This is another example from the breeding program from Honduras. It's called FIA 18, and it's a dessert banana that is in between a regular banana and a plantain. So it has a very funny flavor. It's tart flavor. We call it lemon banana. It doesn't brown at all. And at some point, we thought it might have some chance of replacing Cavendish, but the flavor is just not there. I mean, hardly anything can beat a regular Cavendish banana. This one, we spotted in a farm in Costa Rica. It's a very nice looking fruit with pink salmon pulp. We thought it might have some nutritional value associated with that. This is something called Pisan Ceylan. To me, it's one of the best flavors there are in bananas. Unfortunately, and probably you'll notice here, the peel tends to split once it ripens. So from the consumer point of view, it has no future, but it's really unfortunate because it's one of the best tastes there are. This is manzana or apple bananas that can be found in some supermarkets in the States. When it's fully ripened, it's really, really wonderful. Obviously, these are for niche markets. These are not for mainstream consumption. And we have what you call a secondary group of exotic bananas. This is just a few of them. This is one of the sweetest bananas there are. As a comparison, the Brix values of a regular Cavendish is between 21 and 22. This one can go up to 25 or 26. Has a very funny flavor I don't particularly enjoy, and the texture is kind of hard. It's like a toffee banana. This one, Brie, it's resistant to one of the worst banana diseases there are in the tropics called black sigatoka or black leaf spot. And the texture is like when it's fully ripened, I mean, you bite it and it melts in your mouth like butter. It's really nice. This is another one. It's a plantain, very nice looking, very high in carotene. It hasn't been introduced in the market as we know. This is the Pinsambungai, which I mentioned is extra sweet. This one, Jengambi, it's quite tolerant to rootworms or nematodes that affects bananas. It has a very interesting flavor. This is a very interesting one. This is called Quaikaibon or KKB. Probably this is one is relative of the Cavendish group that was domesticated first in Southeast Asia, but because of the size, it's smaller than a regular Cavendish, but from the flavor point of view, it's pretty similar. This is a Hawaiian plantain. It's a very fat fruit, but very nice in terms of flavor. Can be eaten baked, fried, or when it's fully ripened. Has a very interesting flavor. This one, Chivas has a very smooth texture and flavor as well, and birds love it for some reason. So they're the best testers for us. And let me go through very quickly. And this is something it's a plantain that is the size of a fig, has the same flavor as a regular plantain, because obviously it's not for commercial purposes. Probably it's consumed in Africa and some other places in Southeast Asia. And I will end my presentation here. Just, I don't want to take some time. So if you have any questions, thanks for the opportunity for inviting me here and talk about banana diversity. The problem with that particular type of banana you mentioned is that the peel is so thin, it's like paper thin, that when it ripens, it scratches very easily. So it's very difficult to put it in a box, transport it across the ocean, and ripen it in a regular ripening room, and sustain the rough handling the consumer does to a banana in a supermarket. So unfortunately, most of these exotics are not designed to withstand the whole marketing chain. I mean, the system that we have now has been built over the years around Cavendish. I mean, the way the boxes are made, the way the fruit is handled, that would require probably a different type of packing, individual boxes, things like that. The problem with these exotic varieties is that the productivity is low, is much lower than Cavendish. So the price in the supermarket would be $1, $1.20 per pound. So the value proposal for the consumer will be a very tough sell, because a consumer would say, why should I pay $1.20 for these, I'm sorry for the expression, crappy bananas, if I have a nice looking Cavendish banana? So every time we propose a different type of exotics, the barrier we face is cost. And even if we can reduce costs, the problem is how we can cater or how we can convince the consumer or lure the consumer to buy something as a gourmet banana. And that's a very tough sell. You might have to come up with some tricks like individual boxes, things like that. I know in the Philippines they've done for the Japanese market, but they marketed bananas in a very nice boxes, $40 per pound. So I don't see Americans paying that much. So that's a particular niche. Probably only the Japanese could afford it.
So Miguel, your boots on the ground in Costa Rica. If we don't find a solution to tropical race 4 for black sigatoka, how long do we have left before we do not see any Cavendish?
Ooh, that's a very tough question. Okay, I'm quite optimistic. We have the tools, we have the commitment, at least in Dole. We are part of a breeding consortium that hopefully in Neckenwood will have a replacement in 10 years. I will twist a little bit your question is, how long would it take for this disease to get the Americas? Anytime. I mean, it could be in 5 years, it could be in 10 years. I would say probably less than 10. We're working on a containment plan across the region, and pretty much every company is following suit, as well as the governments, because they know there's a lot at stake. Now, in regard to a replacement, the clock is ticking, and I think we should be we should get ready with a replacement or a hybrid in less than 10 years. Now, this isn't going to be a doomsday scenario. It's not like it's going to be introduced in a matter of 5 or 10 years, there will be no bananas. It will be something gradual. People will try to adapt. Farms that are less prepared or have no containment plans will probably get lost very quickly. So it'll take probably 10, 15, or 20 years before we go to a critical point. In the meantime, or before we get to that point, we have to have a replacement ready. What I see in the future is probably different companies will come up with different solutions, different hybrids. Some might look like Cavendish, some might look like 60% Cavendish, and it's going to be a gamble if the consumer would like or accept that. I mean, the problem is Cavendish's bananas are so good, so predictable, and so easy to consume that proposing the consumer something else, it'll take some time. But going back to your question, how long will it take? My guess is we have to be ready between 5 and 10 years, and with the replacement between 10 and 15 years. But it will happen, that's for sure. Yes? Say it again.
So what strategy are you using to make sure that the new variety doesn't become the same taste as Ghost Michelle and
You hit a nail. One of the questions is, okay, you have a replacement. You switch from one monoculture to another monoculture, and thus you create the conditions for the next problem. Well, if you ask a plant breeder, he or she would say, no, let's try to combine as many varieties as possible in one single plantation. And makes a lot of sense from the pathological and genetics point of view. They would say increase the diversity in order to make the pathogen life more difficult. From the agronomic and production point of view, that proposal is very tough because you need very predictable productivity throughout the year. So you need the same variety, the same attributes. So those are opposite views. My guess is that we will switch from one monoculture to another, but with a difference. In the last 15 years, there has been a lot of emphasis on promoting practices that increases soil diversity. I mean, microbial diversity, boosting microbial activity, using microbial inoculants, or what they call beneficial consortium into the soil, using suppressive soil conditions, things like that. It's very complicated. You need metagenomic analysis in order to understand what it takes for make a soil suppressive. But I'm pretty optimistic that we can crack the code, and eventually we can combine a monoculture with large diversity in the soil. I don't see at this point, from the industry point of view, a mix of different varieties because you lose economies of scale.
In those areas that you were showcasing where there's no bananas growing, has there been any efforts to grow resistant varieties in those areas that aren't in use?
Good question. Remember I mentioned the Taiwanese came up with some, what is called some clonal variants. They can produce for at least 3 years. But it's a tricky proposal. What they're doing is, in order to keep growing or producing bananas in those areas, they introduce these monoclonal variants. The first year, they lose 20% of the crop. The second year, they lose 50% of the remaining 80%. And by the third year, you barely get to 30%. So it's not a long-term solution. It's a fix. It's a short-term fix, waiting for something to happen. What is happening in the Philippines is they're switching to clean areas and abandoning infected areas, or using this approach. The problem with that is the production will be so expensive that the economics will not be there. So most likely farms that engage into that sort of practices eventually will go bankrupt because they wouldn't be able to afford it. Thank you very much. Very appreciate it.